Hello and welcome to this next lecture on acoustics. Today we'll start by looking at the spherical harmonic orthogonality. So first of all, the spherical harmonic is given by ymn theta comma phi is equal to the square root twice n plus 1 by 4 pi n minus m factorial by n plus m factorial p m n cos theta e to the power of I m phi. That is the spherical harmonic. Okay. The orthogonality relation, is given by integral 0 to twice pi d phi integral 0 to pi y m n of theta comma phi y m dash n dash theta comma phi conjugate sin theta d theta. Now if we substitute this here, is going to look like this: integral 0 to twice pi d phi integral 0 to pi square root of twice n plus 1 n minus m factorial by 4 pi n plus m factorial p m n cos theta e to the power I m phi into square root of twice n dash plus 1 n dash minus m dash by 4 pi by n dash plus m dash p m dash n dash cos theta e to the power of minus I m phi because of the conjugate sin theta d theta. Now we have a phi integral, and phi appears only here and here, so we will do the phi integral first. Okay. So if we do the phi integral, I have 0 to twice pi e to the power of I m phi e to the power of minus I m dash phi d phi. Okay. Now if so, case 1 is when m is not equal to m dash. If that is the case, what I have is integral 0 to twice pi e to the power of I m minus m dash phi d phi, which is equal to e to the power of I minus m dash phi I into m minus m dash twice pi. Now m is an integer, m dash is an integer, they are not equal, so this is an integer. Okay. M minus m dash is an integer, and therefore if I take phi to be twice pi and phi to be 0, then both values are same. Okay, it's like e to the power of I n phi, n is an integer in the limit with limits 0 and 2 pi. Okay, so therefore this goes to 0. So this goes to 0 is equal, let me just say, is equal to 0 when m is not equal to m dash. The second case is when m is equal to m dash. Okay, if m is equal to m dash, then this entity is e to the power I 0, so which is 1. Okay, so now I have an integral which is 0 to twice pi of d phi, which is twice pi. Okay, so we will call it twice pi delta m m dash. Okay, so if I bring twice pi delta m m dash into this integral now, then m and m dash have to be same. Okay, so let me copy this. So in here, when I bring in twice pi delta m m dash, so what happens is this d phi integral is done. Okay. And in here the m and m dash have to be same. So I will remove the dash. Okay. So this is what we have ended up with. Now we have to do the theta integral. We do now the theta integral, and I will need this also, so I will copy this. Okay, so now we will do the theta integral, and what is the orthogonality on PMN cos theta. Okay, so that we have 0 to twice pi PMN cos theta PMN dash cos theta sin theta d theta is equal to 2 over 2n plus 1 n plus m factorial by n minus m factorial delta n at n dash. Okay. So now if we do that, n and n dash have to be same. So this n dash and this n have to be same. So this n and this n dash have to be same. So we get twice n plus 1, twice n plus 1, the root here and the root here, divided by 4 pi. Okay. Then I have n minus m factorial by n plus m factorial. Both the roots are eliminating the square root. Then I have this relation which is 2 by 2n plus 1 n plus m factorial by n minus m factorial, n and n dash have been taken care of, and I have twice pi from the phi integral. That is important. Okay. So this goes with this, this goes with this, I have this going with this, I have 4 pi on top, I have 4 pi in the denominator, so that gives me 1. Okay. So this okay, so this relation is correct. So what is that? That relation is integral 0 to 2 pi d phi integral 0 to pi y m n of theta comma phi y m dash n dash theta comma phi conjugate sin theta d theta is equal to delta n n dash delta m m dash. Okay, so that's the orthogonal relation. Now we have some more relations that are maybe useful. So one is this y of minus m n theta comma phi is minus 1 to the power m y m n theta comma phi conjugate. Okay, so nothing changes, only the sign is accounted. Sign changes, that's important. Okay, this is also an important result. Next, what we have, let's just look at a few of these. Okay, so let's say, or do we have y m n of theta comma phi. Okay, so for m equal to 0 and n equal to 0, which is y 0 0 theta comma phi, that's equal to 1 by square root of 4 pi. Okay, so let me just pull it a little bit to the left. So if I have now m equal to minus 1 and n equal to 1, then I have y minus 1 1 theta comma phi, that is equal to e to the power minus I phi square root of 3 over 8 pi sin theta. Okay, whereas if I have m equal to 1 and n equal to 1, I have y 1 1 theta comma phi, that is minus e to the power of minus I phi square root of 3 over 8 pi sin theta. Okay, similarly, if I have y m equal to 2 and n equal to 2, I have 3 let's see, I have y to 2 so this is not minus I phi, my mistake, this is okay. I have a conjugate here, so I have to take care of it. So this conjugate is becomes plus. So y22 is 3 e to the power of 2I phi square root of 5 by 96 pi sine square theta. And if I have m equal to minus 2 and n equal to 2, then y minus 2 is equal to 3 e to the power of minus twice I phi, same 5 by 96 pi sine square theta. Okay, and so forth. And what's important is if we have m equal to 0, then y 0 n of theta comma phi is equal to square root of twice n plus 1 by 4 pi p n cos theta. Okay. So, this also worth noting somewhere. As I said, when we go to solve problems, we will collect all of these and put it in one place. Okay. Now, the Bessel's equation. The spherical Bessel equation. Spherical Bessel, let me call Bessel functions, spherical Bessel functions. Okay. So, we found out that the solution was given by solution, the R of R was given by, okay, a n j n of k r plus b n y n of k r. Just check what I wrote. Oh, R1 R2, okay. Okay, so okay, we'll do that. R1 R2 or R3 spherical Hankel function of the first kind plus R4 spherical Hankel function of the second kind. So, we will look at these spherical Hankel functions. Okay. They are related to the cylindrical Hankel functions. Okay. The spherical Bessel or spherical Bessel, let me just say, are related to cylindrical Bessel. Or Hankel. At this point is not so important, but okay, how they are related, standard books will have it. Now, one thing is between the Hankel functions, h n of the second kind is equal to h n of the first kind x conjugated. Okay. Now, let us just look at the spherical Bessel functions first, okay, how they behave. So this is, let us say, x, okay, and I am plotting, let me take a bigger axis. This is x and I am plotting Jn of x here. So the first one, which is n0, okay, starts off at value 1, it comes down. I am not being very scale conscious, it decays away. It is a now a decaying sinusoid. Mainly it starts off at 1 with 0 slope, okay. This is n equal to 0, okay. If we plot n equal to 2, then it much slower. If you look at n equal to 4, it is even more slower. By slower, I mean oscillations happen over longer scales of x. I am just not being very accurate, but that is, so this is n equal to 2, this is n equal to 4, and so forth, okay. These are Jn's, okay, and they are pretty well behaved, most of them, I mean all of them. The first one starts off at 0 with 1 with 0 slope, all others start off at 0. In contrast, if we look at the Yn's, these are now Yn's, okay, and they will start off at minus infinity, again not to any scale, they come down go off, n equal to 2 comes from minus infinity and starts to approach the y axis. This is n equal to 2, this is n equal to 0, similarly n equal to 4, okay. So all of them come from minus infinity, okay, at x equal to 0. Okay. So now if the radius r goes to 0, okay, we have yn of kr. If the radius goes to 0, then yn of kr goes to minus infinity, okay. So in the problems where the radius, the origin r is equal to 0 is included, we cannot have a yn, so r2 must be 0. So that is the nature of Jn's and Yn's, okay. Now what about the, how do we generate, okay, how do you generate? The generating functions are these. For Jn's, these are minus x to the power n 1 over x d bar dx. The operator to the power n operates on sine x over x, okay. If n is 1, this operates once. If n is 2, this operates twice on this function. That's how it works, okay. Then yn of x is equal to minus x to the power n 1 by x d by dx to the power n cos x by x. And the Hankel function of the first kind, is equal to minus x to the power n 1 over x d over dx to the power n, okay, e to the power ix over ix. Okay. So, this is the Hankel function first kind zeroth function. Okay. And just to see what these are, J0 of x looks like sine x over x. That is why at x equal to 0 we have value 1. Then J1 of x has minus cos x by x plus sine x by x square. Okay. Then J2 of x is minus sine x by x minus 3 cos x by x square plus 3 sine x by x cube, and so on. Whereas y0 of x is minus cos x over x, y1 of x is minus sine x over x minus cos x over x squared, and so forth. Similarly, the Hankel function 0th order first kind is e to the power of ix over ix. Okay. So, if I have the time if I take the time dependence as e to the power I omega t, then this is e to the power I omega t plus ix. So, this is an incoming wave. This will be an incoming wave. Okay. Then Hankel function first kind order 1 is I plus x, and so forth. Okay. There are few more important relations that we need during our solution process. One is Jn of x yn dash x minus j dash n of x yn of x is equal to 1 over x square. We need this some point. Then Jn of x hn dash 1 of x minus j n dash of x h n 1 of x is equal to I over x square, I by x square. Okay. So, for large arguments x going to large values, h n of 1 of x is approximately minus I to the power n plus 1 e to the power I x over x. Okay. And there are a few recurrence relations, which is recurrence relations, which is twice n plus 1 by x h n of x is equal to h n minus 1 of x plus h n plus 1 of x, and h n dash of x is equal to okay. Of these, the important ones are this. We will need this at some point. As I said, at the next class or so, I will collect all of them so that it is easy for us. Okay. So, I will stop this lecture here, and we start by looking at solutions to some simple problems in acoustics in exterior sound fields. Thank you.